This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. We're diving into a fascinating paper today that challenges conventional wisdom in large language model training. It suggests that smaller, less powerful models might actually be the key to building better reasoners. What initially struck you about this research?
The counterintuitive nature of it. We're used to thinking bigger is better, especially with LLMs. More parameters, more compute, that's the usual recipe for success. But this paper argues that focusing solely on powerful models for data generation might be computationally inefficient.
Exactly. The title itself is provocative. It claims that weaker models, when used strategically, can yield superior results. How does that even work?
It's all about the trade-off between model strength and the number of samples you can generate within a fixed computational budget.
So you're saying that a weaker model, while producing less accurate individual samples, can generate many more samples overall? Let's unpack this compute-matched sampling. The paper emphasizes that it's not about simply comparing a weaker model to a stronger one with the same number of samples. Can you explain the crucial difference?
Absolutely. The key is to match the computational cost, not the number of samples. If a stronger model, SE, takes, say, 3 times the compute of a weaker model, WC, per sample, then you can generate 3 times as many samples from the WC model for the same overall cost.
That's a critical point. So instead of comparing 100 samples from each model, you're comparing 100 samples from the SE model to 300 samples from the WC model.
Precisely. This changes the game completely. The paper shows that this compute-matched approach reveals a different picture of the relative strengths of the models.
The paper evaluates the generated data using 3 key metrics: coverage, diversity, and false positive rate. Can you elaborate on what these metrics represent and how they differ between the WC and SE models?
Coverage measures how many unique problems the model can solve. Diversity measures the number of different correct solutions it can find for a given problem. The false positive rate is the percentage of solutions that get the right answer, but through incorrect reasoning. The study found that the WC model, due to its ability to generate more samples, often exhibited higher coverage and diversity. However, it also had a higher false positive rate, reflecting the lower quality of individual samples.
So it's a trade-off. More quantity, potentially at the cost of quality. But the paper argues that this trade-off is beneficial. And the researchers then explored 3 fine-tuning paradigms: knowledge distillation, self-improvement, and a novel weak to strong improvement setup. Can you describe these and the results?
Knowledge distillation is the standard approach. A smaller student model learns from a larger teacher model. Self-improvement involves a model learning from its own generated data. The novel weak to strong improvement involves using data from a weaker model to improve a stronger model. Across all 3 paradigms, the paper consistently found that models fine-tuned on WC-generated data outperformed those trained on SE-generated data.
That's a remarkable finding. It suggests that the sheer volume of data generated by the WC model, even with its higher error rate, outweighs the higher accuracy of fewer samples from the SE model. The experiments used the math and GSM 8K datasets. What were the key findings from these experiments?
The results were remarkably consistent across both datasets and all 3 fine-tuning setups. In compute-matched comparisons, models trained on WC-generated data consistently outperformed those trained on SE-generated data, sometimes by a significant margin, up to 31.6% in some cases.
That's a substantial improvement. Did the researchers investigate why this happens?
Yes, they explored the role of coverage and diversity. They found that both are crucial for training strong reasoners, and the WC model's higher coverage and diversity, despite its higher false positive rate, seem to be the key factors driving the improved performance.
The paper includes several ablation studies. What did these reveal about the robustness of the findings?
The ablation studies confirmed the robustness of the results. They showed that the benefits of using WC data held even when reducing the dataset size or using different sampling strategies. They also demonstrated that both high coverage and high diversity are important for optimal performance.
So it wasn't just a fluke. The results are quite stable. The paper also extends the findings to state-of-the-art models like Gemini 1.5. What were the results there?
Using price as a proxy for compute, the results mirrored those from the earlier experiments. Models trained on data from the cheaper Gemini 1.5 Flash WC consistently outperformed those trained on data from the more expensive Gemini 1.5 Pro SE. This suggests that the principle extends beyond the specific models used in the initial experiments.
A significant portion of the paper addresses scenarios where ground truth labels are unavailable. How did the researchers handle this challenge?
They explored two approaches, one where they used no verification of the generated solutions, and another where they used a language model as a verifier to filter out incorrect solutions. The results were more nuanced in this case, with the advantage of WC data being less clear-cut when no verification was used. However, even with model-based verification, the WC model often still showed competitive performance.
So the absence of ground truth labels complicates things, but doesn't entirely negate the potential benefits of using WC models. The paper also investigates the use of WC and SE models for instruction following tasks. What were the key findings there?
The results were quite striking. Even without the clear notion of a correct answer, models trained on data from the cheaper WC model significantly outperformed those trained on data from the more expensive SE model. This suggests that the benefits of compute-matched sampling from WC models extend beyond purely reasoning-based tasks.
The paper concludes by discussing the future implications of these findings, particularly in light of the narrowing performance gap between smaller and larger LLMs. What's the significance of this?
The authors point out that smaller LLMs are rapidly improving, and the performance gap with larger models is shrinking. This makes the compute optimal approach of using WC models even more compelling. As smaller models become increasingly powerful, the cost savings and efficiency gains from this approach will become even more significant.
So, to summarize, the paper presents a compelling case for rethinking the conventional approach to LLM training. It suggests that focusing solely on powerful models for data generation might be computationally inefficient.
Exactly. The research demonstrates that a compute-matched approach, leveraging the ability of weaker models to generate a larger volume of data, can lead to superior results in training LLM reasoners. This is a significant contribution to the field, offering a more efficient and potentially cost-effective way to build advanced reasoning capabilities.
It certainly challenges the status quo and opens up new avenues for research and development in the field. That was a great discussion. Thank you for sharing your expertise.